Okay, so hello everyone, mainly for the recording watchers. Today I'm going to present this interesting paper that's called TransTab. It's a paper from 2022, and the title says it's learning transferable tabular transformers across tables. We will see in a moment, but this paper focus on changing the tabular paradigm to make it more flexible in order to learn better data representation and allow us to leverage information from different sources, continuously learn, and uh, don't stay so confined on the rigid tabular framework that we all know very well. So yeah. So about the paper, it was originally published in September 2022 for this conference, 3060 Conference on Neural Information Processing Systems. And from these two researchers from the Illinois University Urbana-Champaign. Yeah, so that's a little bit of context. So before we dive in directly into the content, just wanted to make some introduction about our learning tabular framework nowadays. So about tabular data, firstly. Tabular data is the most widely used data format in machine learning. Yeah, I think that's where it originally, from the perceptual model, like from where it was originally applied, and most of our day-to-day problems we use tabular data in order to make predictions and use models to learn and to use as well. And also, we have lots of tabular data nowadays. We here in CloudWalk know very much that we have like lots and lots and lots of data, and all of them are structured, which can be good but also bad. Tabular data requires heavy data cleaning for it to leverage information from different tables and to use it with different columns. So you spend a lot of time formatting your data, merging, dropping things, and sometimes you make mistakes in those steps. And sometimes you assume some things that can lead to broken models afterwards. So this part of the tabular learning paradigm is not very pleasant, and it also brings a lot of problems to our pipelines. And the last thing about tabular data is that most models often assume that the table structure keeps fixed in training and testing. So yeah, when we calculate features and when we train our model, maybe afterwards then we will learn that we cannot like have all the information that we assume that we would have in production. But the model needs it to be constant. Sometimes we do some data filling and scaling and some transformations, but we need to agree with this prerequisite from tabular learning. And about data structure in general in machine learning, we have other areas like computer vision, where the basic elements are not lines in a table or rows in a table. The basic elements are pixels or patches, which are like regions of the image. The pixel is the most indivisible unit, but yeah, you can have like bigger ones. And in natural language processing as well, you have like the basic elements as words or tokens, could be like sentences or something bigger as well. And in the tabular domain, it is natural to treat cells in each column as independent elements, like for our basic elements in our construction. So as an introduction, like comparing those areas in machine learning and AI in general, before we try to understand what the paper is trying to do here. So for the objective of the paper, what the authors try to do here is propose a way to contextualize columns and cells in order to allow the model to learn from tabular data with a flexible data structure. So we want to overcome this difficulty of rigid table structure and try to feed the information without this rigidity, allowing the model to learn just the information and not actually like the data structure itself, if we can say it like that, put it like that. So we take a table-like format, and the paper tries to convert the information to a sequence input. So instead of having like a table where a man on a column is a 0 and a woman is a 1, then we can like feed the model with this information translated as gender is woman. So the model will understand what we are trying to say, but from another format. And the paper argues that this protocol is generalizable across tables and enable models to operate across different table sets. So if we have this information of men and women and gender in different tables, then feeding it in the way that the paper will propose will be better, because we don't have like to guarantee that we have the zeros and the ones, and missing information is what we do with missing information. So yeah, let's see if this generalizes, as they say. So here is one quick example of trying to understand some applications of this framework. So originally what we do is vanilla supervised training. We have our train set, we have our columns T1, and we have our label, that's Y. And then we apply to the same columns T1 on a test set with the same label Y. Or we could also have like a fixed table pre-train and fine-tune, like we just train on T1 columns with their formats, and then we fine-tune for the T1 with the label. So we learn the representation of the data, and afterwards then we do a fine-tune to do the supervised task that we originally wanted to do. So the paper argues that the framework can be used to learn to do transfer learning across tables. So we can operate with different table structures, like we have T1 on columns on the first table and T2 columns on the second table, but with the same label. And afterwards, then we can like fine tune and still learn and apply the same model to those two different sets of columns for the same label. It also says that can do feature incremental learning, that is adding more tables to the original T1 columns. So like concatenating tables and adding more columns, but keeping the task will improve the model, or at least allow the model to be applied in more scenarios. Another operation would be like to do something similar, but where you just learn T2 columns, but you don't know exactly the label in these T2 columns, but you know the label for the T1 columns, and then you fine tune for a third set of columns that is T3, because you learned from those other tables and columns. And finally, something that would be like the most challenging is zero-shot inference, where you have trained your model in multiple sets of columns and tables for the label, and you do a prediction on a third set of columns on a third table without training or fine-tuning, something that the GPT and other large language model do nowadays. So like you can ask for the model to predict something that it has never seen based only on the other information that it had learned. So those are some applications. Seems kind of magical, but we'll see how they achieve or format the data in order to achieve these possibilities of usage. So okay, here just have like this describing what I have already described. I think I'm gonna go through more quickly. So like I can publish the presentation later, and yeah, I don't have to repeat it here. Okay, so let's go to the methodology. The model is mainly divided in two parts, which would be the featureizing pipeline, and I think that's where most of the flexible data structure comes from. And afterwards, the VPCL, which stands for vertical partition contrastive learning, and is where like the magic happens. How the model learns is due to this to this contrastive learning application. But yeah, let's go bit by bit. So in a more general fashion, what we have like our tabular feature data. We have the input table here. Then we go through an input processor, which creates a sentence of semantically encoded tokens, as I have said previously, like gender is something, or I don't know, other information is encoded as a sequence and not as a table. Afterwards, it goes through a gated transformer. We all knew that transformer was coming. But it has this adaptation, which is it adds a gate on the output of the transformer model. I will present it briefly, but the main point of this presentation is not to explain the transformer model. But yeah, we'll see a little bit of that. Then finally it goes to a classifier plus projection, where the VPCL happens with this positive and negative sampling for learning rich embeddings, and I'll go more in detail of how the sampling happens in a bit. And finally, it applies like the supervised or the contrastive learning on the projector or classifier. Cool. So this is the general structure of the framework. Seems very complicated, but I have tried to break it down and try to bring it more familiar machine learning terms, so everyone can understand the general concepts. And the more in-depth details, maybe we can discuss afterwards. But yeah, we have originally this input processor, and we will dive into it later. We have the gated transformer that I mentioned, and finally the learning steps with the supervised and contrastive learning parts. Yeah, so three main steps here. Just note that the input table is on the beginning with our category and binary and numerical features, and then we do something to them. So yeah, let's talk about the input processor. And here we'll talk about our three main types of features and also how we will concatenate them in a sequence format. The input processor will take categorical textual features, and we'll concatenate the column name with the feature value. So the gender example is a good one. So it will take the column name, which could be gender, and then the value, which is woman, and then we'll say gender is woman. So that's kind of simple, like forming a phrase. Cool. For the binary feature, the input processor will do something different. It will, if the feature is 1, which stands for if the feature is present on our data, then we will tokenize that feature and add it to the embedding. And if it's not present, like the number is 0 for the binary feature, it will not be processed to the subsequent steps. So let's say one of us does a PIX transaction, and like we have this CNPJ CPF feature, which is encoded in a binary format. We will only add like the CPF name of the feature if we are a CPF person. If we are not, then we will not add it to the model. The paper argues that this design significantly reduces the computational and memory cost because it doesn't add like lots of sparse one-hot features, and also contributes to making the dimensionality of the data smaller. And finally, for the numerical features, what we will do is not do what we did for the categorical ones. We will not concatenate the column name with value names. What we will do is embed, and the paper said that we will not do that because apparently this was notoriously known to be bad at discriminating numbers. So if we added like amount equal or amount is 15, apparently it's bad for encoding the amount and understanding what's the meaning of this information. So instead, the paper proposes that to process those two information separately. So num, which is the name of the column, is encoded the same as category. So we have the name of the column encoded, and sorry, yeah, I thought that I have added this, but I did not. But then we only embed the column name, and then we multiply by the number value. So if amount is 15, then we embed the amount portion of the feature, and then we multiply by 15 in order to add the numerical information to the embedding itself. And finally, what we do is we concatenate this everything, all these embeddings and informations, and we also add this CLS token to the embedding. And CLS here stands for a token which is used for sentence classification in NLP. So it's like adding the label of our data to the embedding in order to add this information also to the model. But we are not using this to like compute the laws explicitly. We are just passing in order to add the context of this sentence that we just created in the whole scheme of things. So we also add this to the embedding. And it's represented as CLS because it's a special token for sentence classification, because we cannot use normal tokens because they are present on the column names and etc. So yeah, we had to take like this out of vocabulary token in order to do that. Cool. So a little bit of mathematical notation here. We have like the concatenation of all these embeddings, the categorical features, the numerical features, the binary features, and the sentence classification token. So reviewing the first part of our framework, we have the categorical being tokenized and embedded together with the value of it. The binary is multiplied by the value. So when it's 1, we add the binary, and then it's tokenized and embedded. If it's 0, then we don't add. And the numerical is tokenized. The name of the feature is tokenized, and then afterwards it's multiplied by its value. Then we just like do normalization, alignment, and we concatenate everything, and we pass it to the next step. Cool. I think this is one of maybe the most interesting part of the paper, and the other parts are more technical, but I think this is a creative way to to allow for more flexible data structure in order to learn about with tabular data. So let's go quickly through the transformer. What we will have here is 2 main components, like the standard multi-head attention block and the gate feed-forward layers, which are the modification that the paper adds here. The important part about the gated layer that the paper argues is that it controls the magnitude of each token embedding before the final linear projection. So it's kind of adding like this secondary attention mechanism in order to increase or decrease the magnitude of each token after it went through the multi-head attention. And we have this as a sequence of val blocks. So that's why we have like this here. And we just like a normal transformer in sequence model, we then take the output of one block and feed to the next one L times, and then it will learn through the attention and multi-head attention mechanisms how to improve and how the data structure of the sentences and the embeddings are related between themselves. More mathematical notation here. So just to show that we have the original multi-head attention here, and the head is defined as the attention mechanism for each query and key, etc., etc. And for the final step, we add the gate multiplied by the attention dimensions. And I think I took this from the paper. I think this is a mistake. I don't think this is a plus, which would be like to add, but this is a multiplication maybe. Or on the next slide it will be different, but yeah, I think maybe the paper did some mistake on this notation or on the image, but yeah, just wanted to point like we are doing this element-wise multiplication between the gate, controlling the attentions, and just adding the normal linear feed forward that the attention and transformer block have. This is the structure, the multi-head attention. So we have the gate layer, the linear layer here, and another linear layer finally. The original transformer don't have like this gate and linear here. It just added linear after the multi-head. Cool. And finally, how we will learn after that. So the magic of the transformer happened. What we do afterwards. The paper likes the self-supervised protocol for their framework. So this is the first thing that they propose. So also they highlight that since the input processor accepts variable column tables, this opens the door for pretraining on heterogeneous tables, as I have mentioned before, like adding data from multiple tables for doing the pre-training steps. And for self-supervising learning, what we are doing is we will take vertical partitions on our tables in order to build positive and negative samples for the contrastive learning. And the hypothesis that they highlight as well, and I think that's interesting, is that powerful representation should be model view invariant factors. Sorry, I read this wrong. Powerful representation should model view invariant factors, which means that it doesn't matter like how you cut your table, like you should learn how to extract useful information from each slice that you took from the data, something like that. Yeah, the idea here is to use contrastive learning to learn embeddings for the data. And since we are taking partitions, the partitions from the same sample are positive here, and from different samples are negative. So if on the table I have this row, which is myself, each time that I choose the columns that represent my row on the table, I will consider them as positives. So let's say that I took the first 10 features, and afterwards I took the last 10 features. Those two will be considered like the same class for the contrastive learning. So I will show just in a little bit, but we will try to make them closer on the embedded space. But if we take partitions from different rows, like let's say that Mateus have a row, then I will consider them as not being the same class. So I will try to project it in a different part of the space. And remember that we are not doing our supervised task here. We are just trying to learn the representation of the data under the hypothesis that we should learn model view invariant factors. View invariant factors. Yeah, cool. So before we show the contrastive laws, we'll just review quickly the cross-entropy laws. I don't know if everyone is familiar with, but the cross-entropy laws is a classification, binary classification laws, usually not a multi-class classification laws, but is popular in binary classification, and is this very complicated formula, but I'll try to summarize it in the following way. So what we have, let's forget about the whole expression. Let's focus only on the fraction. So what we are doing here we are taking x, which is our prediction from the model, and we are applying we are doing the exponential of x. And on the denominator, we are taking the summation of all the exponents of all other x's that we have predicted. So let's say that we have two classes. The x's on the denominator should try to sum to 1, like if we have applied like the probability of being all of one class is 100%. So if we have like two classes, we would have like 10% of the negative class and 90% of the positive class. So this is our denominator. We are just applying the exponential before summing, which is just a formality. But let's interpret the denominator as our whole probability of our, or at least our whole value for being of all classes. And the top part is just our prediction. So this denominator is trying to translate how much of our prediction we are concentrating on one class. Let's interpret a little bit that way. We applied the log here. We don't need to pay attention to that yet. Oh yeah, let's go to the log. I can show this plot. The idea is that if we have lots of this log is being applied to a number between 0 and 1. That's important. So if we go to 0, this number gets negative and gets negative quickly. Like log of 0.1 is negative. The absolute value is bigger than log of 0.9. So like this graph, the function increases fast when we go near 0. We just have like this negative before the summation because the log of 0 of the number will be negative. So we want, what you're trying to do here is penalize if we have this fraction small for our class. So remember that I have said like this fraction is trying to explain how much of our prediction is accumulated in a class. If this is our class and we have lots of certainty that it's not from our class, this fraction will be closer to 0, which will penalize the model more. I think that's kind of hard to explain the cross-entropy loss, but we can like summarize of being the concentration of our predictions, and if it's the right class, we don't penalize the model, but if it's the wrong class, like we sum this term, which is exponential, and then we penalize the model a lot. So we can see like this behavior of the log loss function. I think that I did not explain that well, but if we can understand this concentration of being the correct class as an important feature for the log loss entropy, I think that's the main point. So what does the cross entropy loss has to do with this model that we are talking here? So they propose the self-supervised loss for our partitions in the following way. Suppose we have the sample xy, and we cut k partitions from it. How are we going to compute our contrastive loss? So we have this expression, which is similar to the log loss, where we have this exponential on the top and exponential on the bottom. And what we are trying to do here is, let's see the denominator first. What we are computing is this function, which is the cosine similarity between all partitions. For B here is all batches. We don't have to pay attention to B because it's just a formality from the library documentation. We can just have the focus on K. So what you have on the denominator is like all similarities summed as by the cosine similarity. And on the numerator, on the top, we have the similarity of two partitions. And which partitions are that? They, for the first part, they will be partitions that are not the same partition. So we take like lots of partitions from one sample, we compute the similarity between all partitions, but we don't compute with the partition itself. But for the denominator, we compute with the partition itself. So what this loss is trying to do is maximize the likelihood of partitions of the same sample being closer or similar, but we don't want it to be just the partition with itself. So if we have k partitions and just the one partition is similar to itself, then it doesn't count. It just counts if all partitions are similar with themselves. It should not be, they should be like spread across all partitions of the sample. This, I think, is the main point of these laws, and very kind of complicated expression to explain, but we can say like this similarity from the cosine, take this and take this understanding that what we are trying to do is maximize the similarity of all partitions from one sample, and not overfit on just one partition being similar and keeping the others not similar on the same sample. We can review this concept later, but I think it's important, like, to show that it's trying to maximize the likelihood of two partitions being closed. In remembering, two partitions are positive here, like they're the same class if they are from the same row, not the same class from our supervised class. Cool, so this is the self-supervised laws. The paper likes this approach much more than the supervised approach that I will explain. So I think that's the main contribution of the paper. That is to this point. Just as an drawing example, we have the input samples with the labels. We don't use the label here for computing the loss. We take, like, we can see like our anchor here is the A1 partition. So our A2 is a positive sample. So we are trying to make them closer on our space. B1 and B2 are negative samples because they are not from the same row. They are from different row. So we try to make them further apart on our embedding space. Cool. So how can we change that to make it use our supervised class? And the paper also argues that this is suboptimal, and may undermine the model transferability. The reason behind this is that tabular datasets vary dramatically in size, task definition, and class distributions. But either way, they show how to do it. So another big expression here. But the only difference is that instead of taking partitions from the same row as positive values and trying to maximize the similarity, they will do this maximization of similarity across rows, different rows, but keeping the same class. So the positives here are samples on the same class instead of partitions of a sample. So that's the only difference. Like from our example, like if I have a row and Mateus have another row on the table, if we are on the same class, then we want to make our two to happen to be closer on the projected space. Cool. So yeah, this huge expression is just to accommodate for the factor that it's introducing the inter row same class to the loss. Yeah. Cool. So that was the part of the projector and the contrastive learning about how we are trying to learn with the data. Yeah, so that covers most of our pipeline. I can go back very quickly in order to review our blocks. So we have our input processor that does those operations. We go through our multiple gated transformers that are fed one after the other. And finally, we go to this projector space with this contrastive loss that's trying to maximize the likelihood of two partitions being closer or two samples on the same class being closer. And for that, it's using the embeddings of the features that we have presented as an input. So let's talk about results, yeah, because it all seems very magical. But let's see if it works. And I'm just gonna do a personal note here. I don't know, but I may think the results here are kind of biased. Let's see. What is the data set that they published the results? They have this clinical trial mortality data sets, which should be available on this link. I access on the link, but there's a form, so yeah, that's where I stopped. But like they have this amount of data points, these types of features, and this positive ratio for their supervised test. So what they're trying to do is like, I think, predict if a subject is going to die or not, because it's that trial mortality prediction data set. Cool. So I think the data sets have those names because this is like data that went through transformations to make it anonymous in order so they don't expose any person's identity here. The first approach is like the supervised learning approach. How does it behave against other vanilla methods? So the baselines they will compare are very common methods for tabular classification, and also some embedding transfer learning models. So logistic regression, XGBoost, MLP, but also VIME, which is the framework that I am using here, and I have presented in one meeting that we have. That is for self-supervised learning from the data and afterwards fine-tuning. Also SCARF and FTTrans, etc. I will show the table. There are lots of methods, but just to point out that they are common. But also want to highlight that TransTab is the only one pre-trained, like trying to understand the data structure before going to the supervised test. The results goes as follow. We have the AUC rock being presented here. The last column is the rank of each method for each data set. They say that they have like done 10 random seeds and etc. to try to make the data more representative. But we can see like that the TransTab method is the best performing one for the AUC rock on all data sets. Other methods, the logistic regression, I think, is the most performing, the second most performing one, and kind of very simple. So yeah, when people say like don't over-engineer things when you have tabular data, like I think that's highlighted here because like logistic regression is very simple against other methods. Yeah, so don't need to talk much more about those details here, but yeah, just wanted to point that out. Cool. So they show that it's the best result. So they will try to experiment with the model in other application scenarios. So they have said that this can be used for feature incremental learning, where you have like your original table, but you add new features. What you do with your model, like you throw it away. In their case, like they argue that you can just add the features and continue training the model. You don't have to throw it away because the model can learn from those features that were added later. So how do you compare that with other methods? So you either drop new features or drop old data when confronting feature incremental learning. So the idea here is that for the other baseline methods, or you're going to throw away some features, or you're going to drop old data in order to test against TransTab here. What they did is they have split the data set in three subsets, 1, 2, and 3. Baseline methods apply to 2 scenarios. The first is learning from all data, but only with features of the first split. Here is I split on the columns of the data sets, not on the rows. And the second scenario is learning from the data of the third subset of features only. And they say they report the best of the 2. So like the A is learning with some features only, and the B is learning. Sorry. A is learning from lots of data, but only with features from one subset, and B is learning only from all features, but only one subset of data. So yeah, they say that TransTab applies to learning from all three subsets because, yeah, the model can, so why not? But the other methods are not doing that. So I think that's kind of a bias, but I'm not sure. Because also their method is like the best performing one. We can see like the logistic regression performing well again. Other self-supervised learning matches like SCARF also perform well with this 5.2 rank. Yeah, but their application for the teacher incremental learning apparently also gives them an advantage because the model can be used on this difficult scenario while the other models cannot. So the other models are kind of penalized because of that. The third and last scenario of learning is zero-shot learning. So you cannot do zero-shot learning with the other baseline methods. What they will try to do is, like, since they established like this, their method is good against the baselines, they will compare the method with itself. So we split the raw data set into 3 equal-sized subsets with distinct columns. Again, as the previous example. Then the model learns from 1 and 2 and is tested on 3 without further training. So 3 have columns that the model has not seen before, and also samples that the model has not seen before. And there are 2 baselines, one supervised baseline where the model learns from 3 and predicts on 3. So that's operating with limited information. And another baseline which the model learns from 1 and 2 and is fine-tuned on 3. So those 2 baselines are kind of not the best application of the model as well, but they are trying to compare with the zero-shot one, so they are applying some kind of penalty to the model as well. And the results are as follow. Like the zero-shot is worse in some cases, but seems to be very close in performance. The transfer one is the best one, like learning from 2 subsets and be fine-tuned on the third one is almost like seeing all the data, so should be better. But the supervised one, which is working with limited data, to have a similar performance against the model that was not trained on the third subset, but have seen the first 2 subsets of data and is doing a zero-shot prediction, which is very interesting. A very interesting result. But again, those numbers are very high, and I don't know, maybe their data set is good for this model and they fine-tuned it well for it. But zero-shot is very hard, and yeah, also like AUC rock of 0.6 on those huge unbalanced data sets is not very impressive. But at the same time, like they are comparing with other methods and it's performing similarly. Cool. So conclusions, finally. Making tabular prediction with a more flexible data structure can leverage information that was previously unavailable or thrown away. Like if you have to retrain your model or choose a new sample or generate new samples each time that you have a change in your work or production environment, they try to be more robust against this problem. VPCL can be powerful to learn useful enriched embeddings, like that idea of the vertical partition is very interesting because you can vary the number of partitions. You can work with partitions with some overlap. You can do lots of things in order to learn the embeddings, like may be very powerful because you can generate lots of negative and positive samples with a set of parameters. So that's very interesting. The method can be used for continuously improvement of the model, even with changing sources of information, like adding or deprecating information. And finally, I think that some results may be biased. I don't know. I want to see more about this model. I want to try it out to see if it is good with our data. Like they have this library. I did not test it yet, but seems easy enough to use. And let's see. Some useful links is the paper publication and the TransTab documentation, the Python library. We can show it afterwards. But that was it. Thank you very much.
Thanks, Gabriel. Really interesting paper, right? Kind of complex, but also the results, right? The idea of being able to change the tables, right, and keep the model. I think this is really, I think maybe what caught your eye, because it's really like.
Yeah, seems good good enough to too good to be true.
yeah, but it shows a lot of potential, right? Yeah. And I think, but one thing that on the result I thought kind of interesting is that like the linear regression performed really well, right? It's not like the gap, like in some data sets, is a bit larger, but it kind of performed well. And it's like the simplest model, and then I think TransTab is like the most over-engineering part.
Exactly.
It's like all the steps that you have to do. I think that was funny. But yeah, I think really interesting. I think the idea, right, of how to leverage transformers. Anyone has any questions or comments for Gabriel?